Okay, so welcome again. I just realized this date I have not changed. So today is the 8th of March. So we'll be in lecture. This is going to be lecture 12. So, and the focus of today's lecture is going to be to look at some applications of this fast polynomial multiplication that we saw. So in some sense, it's okay even if I think the last class was very dense. I mean, like there was a lot of things that we did in the previous class. But it's okay even if you didn't follow a lot of it, because you can just take, I mean, we'll be using things from the last class only as a black box this time. Okay, and we'll see a few applications of, just say that we know polynomial multiplication can be done in this much time, and we'll just see, okay, what does that mean? What else can we do in that time? So that's what we're going to focus on today. And in the process of looking at a few applications of polynomial multiplication, I mean, we'll again need to go over some rings and ideals, because this is going to play more and more of a role in the next few lectures. And hopefully, as a part of what we are doing today, we will learn one extra very, very important tool, which will again end up getting used. And I'll mention this when we get there. Okay. So just a brief reminder, I mean, like, I don't know if everybody who intended to submit the problem set has submitted. Like, I had put up a thing on Academy that if you want to, I mean, I'm okay with reasonable delays, but the onus is on you to send me whatever you have by email, even if you plan to submit it later on. I mean, so yeah, okay. So before that, I'll also want to correct one mistake I had made. I mean, at some point I will just write down the full exposition for the Schonage-Strassen algorithm. I think last time I incorrectly claimed that the weaker algorithm we did in class, if you solve the recurrence, you get n log n 2 to the order log star n or something. I actually did the calculation and turned out that what you get is n polylog n. Okay, I mean, if you solve the recurrence, that's what you end up getting. So it's worse than what I thought was the algorithm we saw last time. But anyway, don't bother too much about it, because at this point, the only thing we're going to be using is the fact that there is some algorithm that does polynomial multiplication in near linear time. Okay. The only thing we'll really care about is that, I mean, from this point onwards, we'll basically say near linear to just mean n polylog n I'm willing to tolerate. And we'll work with algorithms of that type. If you really want to nail the details and so on, you need to look at Schonage-Strassen's, the full proof, which I'll hopefully put up an exposition at some point. And towards the end of the class, we introduced the idea of generally looking at ideals and quotients, because that was a way of formally adjoining an element to a ring. Because the way the proof worked last time was we wanted to do an FFT-based polynomial multiplication. But in order to do an FFT-based polynomial multiplication, you needed some principal root of unity. And maybe your coefficient space does not have that root of unity. So you artificially add one. And the process of artificially adding one was done via a suitable quotient. Okay. So to begin today's lecture, I'm going to just go over ideals and so on, and just get familiar with these sort of ideals and quotients a little bit more. And hopefully today's application will make you a bit more comfortable with these ideals and quotients. Okay. So what is an ideal? An ideal is a subset of your ring R that satisfies the following two properties. So firstly, it is closed under your usual ring operations, which is whenever you have two A and B that belong to your ideal, then their sum, their difference, and their product all happen to fall in the ideal as well. Okay, which in particular also means that 0 must be in the ideal, because A minus A must be in the ideal. Okay, but something which is perhaps a bit more important is the fact that even when you multiply by things outside the ideal, you stay in the ideal. By that, what I mean is if A is an I and R is an arbitrary element of R, this R could be outside of I. Okay, you still want that A times R to be inside I. Okay, so that's the two properties that you want. And roughly speaking, it plays the role of what a normal subgroup is for groups, in the sense that they are kernel-like objects. I mean, they behave like kernels. Okay. And a few examples that we saw was, look at, suppose your ring R was the set of all integers. Then an example of an ideal could be, let's look at all multiples of, I don't know, some number, 42 or something. Okay. So this ideal is referred to as 42Z. I mean, just to mean that, it's basically all multiples of the integer 42. The other one could be you look at all, I mean, maybe the ring is your ring of polynomials in one variable. And the ideal corresponds to the set of all polynomials that on 7 evaluates to 0 or something. Okay. And there are some which are a bit more non-trivial, which is like maybe these are, you're working in the ring of bivariate polynomials on variables x and y. But now you say that I'm only interested in polynomials where if I look at every monomial, either it is divisible by x squared or is divisible by y squared. I mean, every monomial has this property. Okay. So in particular, you can't have a monomial which is just x or just y or just xy. So it only involves all the other monomials, so to speak. So that could be one such example. And you can verify in each of these situations that it actually forms an ideal. Okay. And we also gave a notion of what does it mean to say something, an ideal generated by something. Okay. So maybe just to get a sense of things, what is a generator for this ideal? If I want to write this as an ideal generated by a few things, what would you want to write here? So I would like to say that this is I is generated by something. So it's just, in fact, it's just generated by 42. So we are basically saying what's the smallest ideal that contains 42? Well, if you have to contain 42, in particular, you need to contain all its multiples because of property 2. And basically that's what captures this. Okay. Now what's the generator for this ideal? So someone, sorry?
There should be like some polynomial, right?
Yeah. So which polynomial should generate everything? I mean, firstly, is there such a thing? Yeah. So it turns out that just x minus 7 generates everything. Because a polynomial evaluates to 0 at 7 if and only if x minus 7 is a factor of it. And this is an example of an ideal that actually is not made up of a single generator, but there are multiple generators. And just by definition, this is basically the ideal of generated by x squared and y squared.
Y squared.
Right? You're saying you look at all possible combinations of the form a times x squared plus b times y squared. So you're forcing every monomial to be divisible by either x squared or y squared. Okay. And so given this notion of what an ideal is, there was this notation that we will start using. And this is a notation you're familiar with anyway. But now we are formally stating what the notation is. We will just say f equals g mod I to just mean that the difference is in the ideal. Because this is what you would do for integers. When you say 42 is 2 mod 10, it just means that 42 minus 2 is divisible by 10. Or rather, 42 minus 2 is in the ideal generated by 10. The ideal generated by 10 consists of all multiples of 10. Okay, so this is just some sort of shorthand notation for what this means. Okay, f equal to g mod I is just shorthand for saying the difference happens to be an element in the ideal. Or in other words, you sort of say if you are okay ignoring elements in I, like if mentally to you elements in I do not matter, then in that perspective, f and g are the same. Because their difference is basically something that doesn't matter. Okay, so that was.
This is basically the same as like these being the same cosets.
Yeah, exactly. It's precisely the same thing. Okay, and once you have this notion, there is a thing of looking at this coset. This is basically often sometimes people put a bar on top, or they'll put a parenthesis outside to indicate the fact that you are looking at this class of all possible elements that happen to be equal to a mod I. Like for example, when you talk about, I don't know, 1 mod 4, I mean, you can maybe think you're thinking of all possible integers such that when you divide by 4, you get remainder 1. Okay, so and it's easy to sort of notice that, you know, F equal to G, if you think of this as a relation that tells you are the two, you know, are they the same mod I or not, it forms an equivalence relation. So this is just what this, I mean, you might refer to as an equivalence class. Okay, it's not particularly important. It's just that, I mean, this object refers to the class of all elements that happen to be equal to A mod I. Okay, and the nice thing about this is that it turns out if whenever I is an ideal, you can start talking about additions and multiplications of these equivalence classes. Okay, and you just define addition and multiplication the following way. You say A plus I, the equivalence class A plus I, when you want to add it to the equivalence class B plus I, the resulting thing is the equivalence class A plus B plus I. That's just definition. I'm just going to define it that way. And similarly, A plus I times B plus I equals A plus B times AB times AB plus I. And the key point is that this happens to be well defined. By that, what I mean is, well, you could have chosen one element here and one element here and taken its product. And that fell in some equivalence class, and you might have defined it to be whatever that equivalence class is. And well defined just means that it doesn't matter which representative you chose here and which representative you chose here, you will still come up with the same answer. Like irrespective of which representative you choose, we will all come up with the same answer. And in some sense, this is something that we've been doing anyway, because we were sort of, if you recall, we were saying things like 0, 1, 2, 3, 4, 5, 6, when we consider mod 7. Okay, we were basically saying here I can define a product operation and stuff like that. What really were we doing? We basically said take a number which is maybe, I don't know, 2 mod 7 and a number that's 4 mod 7. You multiply them and you're defining it to be 1 mod 7. But the point is, you need to spend a little bit of time to sort of say it doesn't matter which number mod that is 2 mod 7 you picked up and which number that was 4 mod 7 you picked up. No matter what you multiply, you will end up with a number that's 1 mod 7. So this product is well defined. Okay, and once you have a nice definition of a sum and product or something, you naturally have a ring structure. And this ring was referred to as this R mod. Okay, so which is why whenever people write something like Z mod 42Z, what they literally mean is that let's look at the possible remainders modulo 42. And on this class, I am telling you how to do addition and how to do multiplication. Okay, so hopefully now the notation is starting to make a bit more sense. Okay, good. So it basically means, when this just means you just think of them as elements in R, multiply them the usual way, but basically ignore any contribution you're getting from I. You don't care about contributions that are coming from I. Okay, and whenever you deal with things like this, just like when we talk about Z mod 42Z, we mentally tell ourselves that look, the numbers are basically 0, 1, 2, 3, all the way till 41. And we are defining a multiplication or addition just on this thing. And what exactly are we doing here? All we are saying is that, look, each of this was some class of elements, some class of possible elements in R, and we would like to choose a suitable representative. And basically say that, whenever I'm talking about this class of elements, I want to somehow think of it as the same as this one representative. So many times it's very convenient to work with one such representative for each class. Okay, so let's look at a couple of examples. So suppose, for example, your ring corresponds to the univariate polynomials with real coefficients. Okay, and maybe the ideal is the ideal generated by, say, x power 5. That is, anything that is divisible by x power 5, in your mind, you don't care. Those are all sort of higher order terms. You don't care about that. So what would a convenient representative for each class be?
So it's like all the polynomials of degree up to 4, right? That's
right. So you will basically say, given any polynomial f, I mean, this f has a long coefficient representation. So there is a constant term, there's a degree 1 term, degree 2, degree 3, degree 4, degree 5, etc. But you're basically saying this entire bit is sort of don't care. Like, because if you think about a polynomial that was only this and there was all zeros here, that is an element in the ideal. So in some sense, I don't particularly care about what happens here. So I might as well put zeros in all those places. So one natural representative is going to be, you just define this, the representative for this to be f0 plus f1x plus f2x squared plus f3x cubed plus f4x to the 4. And beyond this, you don't care. So you're only dealing with degree 4 polynomials. Okay. And your additions and multiplications are going to be, you add stuff the usual way, component wise, like each coordinate gets added up. But multiplication, you multiply two such polynomials, and whenever you get a term that is beyond x power 5, I mean x power 5 or more, I mean, you just throw that away. You don't care about those things. So did that make sense? I mean, so yeah, okay, good. So this is what I mean by saying you choose just one representative, one convenient representative of the class, so that you can just deal with those representatives as opposed to the class in its entirety. Okay, good. So now let's do the following thing. Suppose your ideal is generated by this one quadratic, x squared plus 4x plus 3. Okay. Now, like Saurabh mentioned last time, the most natural thing to do is to basically saying that, look, whenever you see x squared, you might as well replace it by 4x plus 3. And if you mentally think of doing it again and again and again, it seems like the representative should just be the linear part of something. I mean, it should be of the form ax plus b, but I want to be more precise. So if I want to write down, okay, x power 5 mod I is one such equivalence class, what would be a convenient representative for this? So what would you do for this?
Just divide we can do the polynomial division, we know, right? So divide
so what do we, so let's just do that at least for a few steps. So we will write x power 5, and what are we trying to do? We are trying to divide x squared plus 4x plus 3 with this guy, and we are literally trying to find the remainder. And we are basically saying whatever is the remainder under this division, that's what I would like to put here. Okay, so let's just maybe do 2 steps of the division so that we all know what we are doing. So what would I do? I have an x power 5 term. This has an x squared term in the beginning. So it makes sense to multiply with x cubed. So you get x power 5 plus 4x power 4 plus 3x squared. And if I subtract the 2, I end up with minus 4x power 4 minus 3x squared. So now I need to get rid of this guy. So I will multiply this with minus 4x squared or something. So then I'll get something, and I'll keep on doing this until I'm left with some term of the form a0 plus a1x. Right? I hope this is the standard division algorithm you would have done in school. And it is this that you want to put as your representative. So in some sense, what you're putting here is a remainder when x power 5 is divided, divided by whatever is this polynomial, x squared plus 4x plus 3. Okay. Now let's ask ourselves, suppose you're working not with Rx, but you're working with Zx. Okay. And this stupid polynomial was 2x squared plus 4x plus something. Now you end up with 2x squared. Now the problem is I have no way of figuring out how to cancel off this x power 5 term, because over integers I don't know how to divide stuff. Okay, so things get a little, one needs to be a bit more careful here. So to avoid complications, I'm just going to define a new, a notion of what is called a monic polynomial. and we will only care about divisions by monic polynomials. A monic polynomial is one where the highest degree term is invertible. Just tell yourself the highest degree term is basically equal to 1. Like something you can divide with. I mean, over integers, the only thing you can divide with are 1 and minus 1. The others don't have you can't divide by those. So we'll just tell ourselves that we'll only be interested in things where whatever you're dividing with turns out to be a monic polynomial. Okay, so just this thing, definition, a polynomial where the coefficients are coming from some ring R is said to be monic if the highest degree coefficient, whatever is the highest degree term in G, that happens to be a unit. A unit just means it's invertible in the ring R. Okay, and in fact, I'll make life even simpler. From this point onwards, we will mostly be dealing with polynomials where the coefficients come from some field. I mean, we needed to work with rings because we were adjoining elements and stuff like that, so things got nasty. But hopefully from this point onwards, we'll only be working over fields. And the nice thing about it is that every non-zero element is invertible. So therefore, all univariate polynomials are monic. Okay, so we don't need to, I'm just telling you this as a technicality, but this will probably never bother us in what we are doing.
But yeah, whenever you are working in like over rings where not everything is a unit, then what, like, how do you deal with it? You just say
so then we'll have to do, we'll actually encounter situations of this sort where we'll have to do some jugaad to make it monic. But whatever I'm going to say right now will be dealing with only things where these complications don't matter. Just give me a minute. Basically, I will define this notion of what is called a Euclidean property, which is something we take for granted. Okay, but I'm just spelling it out. And this Euclidean property just means I give you an F and I give you a G, and I promise to you that G is monic. Then whatever division algorithm we ran right now, this thing of slowly doing whatever, what did it eventually tell you? It told you that there is a unique way to write F as Qx times G of x plus R of x.
Why monicness is important?
Sorry?
Why monicness is important?
Because if this was 2, I don't know what I need to put here to cancel off x power 5. If the 2 was not invertible, then I can't cancel off arbitrary terms.
Oh, since you are in ZX, I see.
Yeah. So that's what I mean. But so in general, the Euclidean property just refers to the fact that whenever you're given F and G with the promise that G is monic.
But but you are doing in RX. That's why.
Yeah. But I'm just giving you this property in general.
I see.
Because I'm going. We are soon going to ask the following task. I give you an F. I give you a G. Can you find out the quotient and remainder quickly? That's going to be the task. Okay. And in order for this, first I need to convince yourself that this quotient and remainder makes sense. Like there is a well-defined notion of what a quotient and remainder is. And we just saw that the standard division algorithm was going to tell you a unique Q and R. Okay. So basically we're saying that I'm given F and G and I want to find polynomials Q and R with the following property that R of x, the degree of R of x is strictly smaller than the degree of G of x. The standard definition of what a remainder is. And this in general is called the Euclidean property that these polynomial rings have. That when I have a monic thing, I can do the division algorithm in some sense. But as we saw above, the algorithm that we wrote down here is not particularly efficient. In the sense that, okay, probably it runs in polynomial time, but we are in a situation where polynomial time is not good enough for us. We want a near linear time way of doing things. Okay, so we would like to know, what do we need to do to solve this question? So here is the task. I'm given F and G over some univariate ring F of x. Okay, or maybe this is just some R of x and you're given the promise that G is monic. Okay, and the goal is to find Q of x and R of x such that this equation is satisfied and R's degree is smaller than the degree of G. Okay, is the task clear to people? Okay. Yeah, so we're going to see an application of the polynomial multiplication algorithm for this. And it's sort of clever, and I don't know how to really motivate this trick that is done. So I'm just going to tell you what this trick is, and we'll just convince ourselves that this works. Okay, so let's take an example, and I'm going to take f of x to be equal to, I don't know, let's say 13752. Okay, and this just means this is the polynomial 1 plus 3x plus 7x squared plus 5x cubed plus 2x power 4. Okay, I'm going to define this notion of what is called the reverse of f. Okay, to just be, you take the coefficient vector and just reverse it. So 2, 5, 7, 3, 1. And since you're reversing, I need to tell you basically, like, you're thinking of it. I mean, are you adding zeros and then reversing it, or are you not adding zeros and reversing it? Right? If I'm not mentioning anything, what this will mean is that you just, I mean, you forget all subsequent zeros that are coming in, and you only reverse the block that you have currently. So this, on the other hand, is going to be the polynomial 2 plus 5x plus 7x squared plus 3x cubed plus x power 4. It's just some syntactic operation. But can I write this in terms of f of x in some algebraic way?
Can you repeat the question?
So I want to say right now, reverse of f of x is some polynomial, some f prime of x. Okay, f of x was some polynomial to begin with. Is there some relation between f of x and f prime of x?
So maybe wait, they are not the same. I thought if we could break this down into saying, if I just want to shift one thing from front to back, then how can we write that? Like,
Actually, I don't know how to do that, but you know how to.
No, I thought
Asif has an answer, which is almost right, but so Asif has an answer in chat, which is to basically say, look at f of 1 by x and then multiply by x. You shouldn't multiply by x, but instead you should multiply by something so that everything gets inverted.
So x to the power 4 into 1 by...
Yeah. So in this case, this happens to be, this is x power 4 into f of 1 by x. Okay. So in general, this is going to be equal to x power n into f of 1 by x, where n is the degree of f. Okay, it's a way of algebraically getting, whatever you want as a result. So is this okay so far? I mean, so it just makes sure that the coefficient of all the terms sort of reverse itself. Okay. So now what we are going to do is the following. We are just going to take this equation. I mean, we are supposed to find what q of x and r of x are. Okay. Instead, we are going to try and reverse this equation and then solve for q of x and r of x. Why we are doing this will hopefully become clear soon. Okay, just bear with it for a while. I mean, I honestly don't know how to motivate this thing if you have not seen the proof. Okay, so let's just write this down. What will this mean? So this, I know this is basically equal to x power n into f of 1 by x, where x is the degree of, n is the degree of f. By the way, let's put some degree bounds here. So this degree, let's say this degree was n. And let's say g was given to us where the degree was equal to m. Okay, so then I know that the degree of q is supposed to be n minus m. Okay, because the quotient will have degree n minus m. And this r of x, I don't exactly know what the degree is, but the only thing I know is that this is strictly smaller than m. Okay, and we are trying to find out what is this q and r. F and g are something that we have at our hand, and I'm assuming that g is monic. And in the sense that I'm assuming that the highest degree coefficient of g is 1 for simplicity. And I'm just going to find out, figure out a way of computing R inverse. So let's do this. And I want to know, how does this equation simplify? So this is equal to, let's just do the, let's just compute this thing, which is like x power n into q of 1 by x, g of 1 by x, plus x power n into r of 1 by x. I'm just syntactically applying this. That reverse of something means you replace x by 1 by x and then multiply by x power. Okay. Okay. Now, fortunately, the degree of q was equal to n minus m, and the degree of g was equal to m. So this x power n I can split as x power n minus m and x power m. Right. So I'm just going to write this as, this is going to be x power n minus m q of 1 by x times x power m g of 1 by x plus x power n into r of 1 by x. Okay. And the first term, this is exactly equal to the reverse of q. Okay. The second term is equal to the reverse of g. Okay. But on the other hand, like this guy, the best I can say at this point is that this is going to be x power n minus the degree of r times reverse of r. Right? This is like one of these situations where there are some trailing zeros. So when you reverse it, it's going to be divisible by some power of x. Okay. Now, here is the part where we are going to, and I'm just going to note that I know that the degree of r is supposed to be strictly smaller than m. Because that's what remainders are supposed to be. Remainders are supposed to be, smaller than whatever you're dividing by. Okay. So this, I'm going to write this. This is the part where our modulus is going to help. Reverse of q times reverse of g mod x power n minus m plus 1. Because basically I'm going to say, let's look at this part. I don't know what this polynomial is, but I basically want to get rid of it. I don't want to worry about those polynomials. But notice that the degree of r is at most m minus 1. So therefore, whatever this quantity is, it is divisible by at least x power n minus m plus 1. Right? So this entire thing is something in this ideal. It's divisible by x power n minus m plus 1. So it's just that I want to basically get rid of this part. So I am going modulo a suitable ideal so that I'm guaranteed that that part sort of goes up. At the moment, it's a completely syntactic thing that we are writing down. It's unclear if any of this is helpful at this point. But I hope at least the veracity of whatever we are doing is clear. Okay. So we started off with, we wanted to solve for q and r satisfying something. I'm going to first try and find q, and then once we find q, we can of course find r by subtracting off q times g. Okay. So now somehow instead, my question boils down to this question. Can I find a q that satisfies this property? Okay. And it's like unclear, why would you be able to, why is this question any simpler than what you started off with? Okay. So here is one leap of faith. Suppose just by some miracle, okay, you could magically find a polynomial h of x such that h of x times the reverse of g equals 1 mod whatever this ideal is. Okay, in some sense, you can invert this, whatever this polynomial is, in modulo this ideal. Okay, then how is, can someone tell me how to find reverse of q?
multiply both sides.
Just multiply by g on both sides. So then this basically means that h of x times reverse of f, this is basically going to be equal to reverse of q, but it is like, it's not quite reverse of q, it is reverse of q modulo this stupid thing. Oh, sorry, this is a plus one. Okay, so you get something. I mean, okay, but the question is, do we have enough information to figure out what q is at this point? Okay, so what does this say? This implies that reverse of q, which is what we wanted, is equal to h of x times, I'm just writing it once again, I don't know why, mod x power n minus m plus 1. I mean, I might avoid writing this stupid whatever angle braces when it's just a single generator and it's clear. Okay, now what do I know about this? I know this is a polynomial of degree n minus m. Okay, because I mean, I'm trying to find what this q is. Okay, so what does this mean? So this says that instead of, this is what I'm supposed to find. Suppose someone told me what h of x is, I know what f is, therefore I know what reverse of f is. Suppose I do this polynomial multiplication. Okay, I might end up with something. Okay, this is what h of x times reverse of f is. Okay, what do I know about reverse of q versus whatever I have computed so far? So if this is the whatever this threshold where this x power n minus m plus 1 degree terms start, okay, what I know right now is that everything here matches the correct value of reverse of q. Things beyond that I have no control. I mean, it could be some garbage that is there, okay, which I have no control. But here is where it's super useful. Fortunately, the garbage starts only after the terms that you want ends. The polynomial you're interested in has degree at most n minus m. This is saying that the polynomial on the right hand side and the polynomial on the left hand side agree on the first up till degree n minus m, but beyond that they could be garbage. So this basically tells you that, okay, just compute this product, just throw away all the other garbage terms. That has to be equal to reverse of q. You don't have a choice, right? Okay, so it's super convenient that somehow the thing that we are going modulo does not affect what you want to compute at. So this basically tells us that we can find this polynomial reverse of q, and hence, I mean, if we can find reverse of q, we can also find q by basically one polynomial multiplication of h of x and f of x. Sorry, not f, but reverse of f. Okay, so is at least, if someone magically gave us this h of x, then is it clear that we have our algorithm that we want? I mean, the algorithm is going to be clear. Somebody magically gives us this h of x. We're just going to compute h of x times reverse of f, and then throw away all the terms beyond x power n minus m. Everything from x power n minus m plus 1 onwards, I just set them to 0, those coefficients to 0. That happens to be equal to reverse of q. So I have basically found q. Once you have found q, finding r is trivial because you just look at r is just f minus g times q. Are things clear so far? So this basically tells us that the time that it takes to find q is basically the time it takes to find h plus one application of polynomial multiplication. And if you want to do q and r, this one is now going to become 2. Because after you find q, you will do one more multiplication and subtract things off. Okay, so we have just completely reduced the problem of finding the quotient and remainder to the problem of somehow inverting whatever this this G was. Like finding an edge such that this is equal to 1. Okay, maybe let's just pause to make sure that we are all on the right page, and then we'll go to see how we can compute such an edge. So does someone want me to repeat the parts of this, or it was something unclear, in which case I'll just go over that again. Okay, so if things are okay, then let's just proceed to this thing of inverting reverse of G modulo one of these ideals. Like, why should one be able to do this? Okay, so the way we are going to do this is, let's just do this by example first to convince ourselves that this is something that is achievable and figure out. So what was I told? I was told that G is a monic polynomial, which meant that the highest degree term had a coefficient of 1. I mean, it was supposed to be a unit. I am just simplifying things and saying that the highest degree term has coefficient 1. So when I reverse G, you're now going to end up with this polynomial instead, which is basically 1 minus 7x. So if the highest degree term for G was equal to 1, this means that the constant term for reverse of G is equal to 1, because they interchange places when you do a reversal. Okay, and now the question is, suppose you wanted to compute 1 minus 7x and you wanted to invert it. What would you do? Okay, and this is something that I guess you're familiar with, and you will just write this as 1 plus 7x plus 7x the whole squared plus 7x the whole cube, blah, 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 because you are familiar with these geometric expressions. Normally, this is not a valid expression at all, because this is like a sum going to infinity. But the key point is, you only care about it being equal to 1 modulo some suitable power of x. Okay, so if, for example, you care about, can you give me the inverse of this modulo x power 100? Well, yeah, you go all the way till x power 99. 7x power 99 mod x power 100. Did that make sense? So at least this is the reason why these inverses seem to, it's reasonable to ask for these inverses. Okay, the reason you are able to do this is because this is what is called a power series representation. But it's one of these things that your modulo is something that lets you truncate off the power series beyond the point. Like, you don't care about what happens beyond that point. So, and this is an honest to God polynomial. Yeah, it has degree 99, which is horrible, but doesn't matter. It's an honest to God polynomial such that when I multiply this with 1 minus 7x, you will end up with a polynomial that looks like 1 plus something divisible by x power 100, which you don't care about. Is this clear so far? This is the reason why we were doing this reversal and going modulo x power this, because somehow, now in hindsight, all of them hopefully make sense. Because this division is something that works only when the constant term is 1. And you needed the constant term to 1, but you only knew that f was monic. So you set it up such that you push that monic, condition to the constant. Okay, yeah, some tricks on top of it. So in general, whenever you have an expression that looks like 1 by 1 minus blah, and you care about it mod x power k.
I have a doubt.
Yeah, go ahead.
So if you just go through the same proof in ZX, you cannot replace x by 1 by x, right? And do the proof.
Why can't I? Again, what do you mean by I cannot replace x by 1 by x?
Means I mean to say that we use the special fact that we x to the power 4 means x to the power n into f of 1 by x, right?
Yeah, this particular thing. Okay.
Yes. So I was wondering, so what fx means? So fx says that if we put the value of x from the field, we'll get an element in field, right?
No, but this sort of syntactically seems to make sense, right? I'm just thinking of it as like whatever x power minus n. Just think of it as a formal expression. If that's what you want. So I'm trying to figure out what precisely here is bothering you. Is it that 1 by x, I can't evaluate it to for x equal to anything?
Yes.
But I'm not going to at all. I'm just thinking of 1 by x as a formal expression. So the polynomial will now end up being 1 plus 3 by x plus 7 by x squared plus 5 by x cubed plus 2 by x power 4. And since I'm now multiplying entirely with x power 4 after I do this division, somehow the denominators cancel off. So all I'm saying is just delay your evaluation until you have an honest to God polynomial and then do your evaluation. But at the, I mean, this is just a formal expression. I mean, like 1 by x is a symbol. That's it.
Okay.
Yeah. Okay. So in general, as I mentioned, that whenever you have an expression that looks like 1 minus blah, where blah is something divisible by x, then you can always invert it using the standard, whatever, your geometric series sum. Because blah power k onwards will become divisible by x power k, and modulo x power k, you don't care about those terms. Okay. And this is the reason why whenever we are dealing with a reverse of G, when G is monic, such an H exists. And in fact, that X is this big sum. But it's just that I want to find it quickly. I don't want to compute this sum as I have written here because that feels too expensive. I want to somehow figure out a different way of computing this inverse quickly. Okay. So here is the subtask. And instead of keeping constantly writing reverse of G all the time, I'm just going to now say I'm given a G of X that looks like 1 plus something. Okay. And I'm given some threshold K. This K is going to play the role of whatever, this N minus M plus 1 or something. Okay. And all I want is I want to find an H of X such that G of X, H of X equals 1 mod X power K. So is the task clear? Okay, so this is just a subtask. In order to solve the division problem, it amounts to solving this particular subtask that we have written. Like it is inverting a polynomial whose constant term is 1. And we want to do it quickly. Okay, and I mean, so here is where I'm going to introduce one very, very important tool, which you may have encountered when you were doing some, I don't know, some optimization course or something. And it will
Horner's rule or something.
Sorry?
Horner's rule or something like that. And
okay, Horner's rule is a way of evaluating a polynomial. And this is a notion of sort of doing, I don't know, these are iterative methods. And this is like a very useful thing to know, where you slowly try to get better and better answers compared to what you had earlier. Okay, things will become clear once you see what happens. So
just a second, sorry. So
yeah.
So we want to get this 1 plus blah squared.
Yeah.
So will this be slow if you have 1 plus blah, and then once you have this,
so that is, and then you keep multiplying by thing and so on. So the number of multiplications you are going to do is going to be like k of them. And each multiplication potentially takes something like n log n log log n time. So the entire thing will end up taking n squared log log n log n sort of a thing. Which at this point we are not going to tolerate. We are like, we want like O tilde of n. That is n, and I am willing to accept polylog factors on top of it, but nowhere close to n squared.
So you want to do something like this exponentiation kind of something.
But even that, I still don't know how to.
Yeah.
I mean, that still will mean that eventually I need to add up all of these things. And that already seems to take an additional factor of n. So, yeah, so that somehow these sort of naive ways of doing it seems to get stuck. So we need to come up with some way of globally figuring out what h is and not somehow compute it term by term. Or rather, term by term, I mean in this. So what we are going to try and do is compute h coefficient by coefficient. Okay. So I don't know what the value of, what h of x is supposed to be. This is going to look like h0 plus h1x plus h2x squared plus blah, 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 blah. And I want to figure out what this h is. Okay. Do I know what h0 is going to be? Okay. So h0 this has to be equal to 1. Okay. So what we are going to do is the following. Suppose I have figured out the first, I don't know, first I coefficients. Can I figure out the next coefficient quickly? Hopefully not the next, but maybe the next several coefficients quickly. So this process is often referred to as Newton iteration or Hensel lifting, whatever. It's a way of successively improving your solution. Okay, and somehow starting off with a stupid solution, but constantly making progress to a better and better approximation. Okay, and that's what we are going to do. Okay, we'll try and find h iteratively. So I'm going to, in general, we'll start off by saying h of 0 is just the polynomial 1. Okay, well, I currently have the property that h of 0 times g, this is equal to 1 mod x. Right? If I ignore all multiples of x, this is something that gets the constant term correct. The rest of it is like, there is just no guarantee at this point. But this is what we're going to do. Right now, I have an inverse modulo x. That is not what I'm satisfied with. I want an inverse modulo higher powers of x. And we are slowly going to try and improve the solution we have at every step. Okay. So we basically are going to ask, okay, here is the solution we start off with. Can I improve the solution in some way? Okay. And in general, let's just assume that, in some intermediate step of the algorithm, you have found some solution hi with the property that when I multiply it with g, I get 1 mod x power I. Okay. Maybe the k that we want is much larger than I. So this is not yet a satisfactory solution. I want something better. Okay. And what we are going to be asking is, can I somehow improve the current solution hi to a better solution? Can I somehow come up with a better solution? Okay. And notice that if you only care about something modulo whatever x power I, this is the same thing as whatever gi times h power I. This is equal to 1 mod x power I, where gi basically refers to, I don't know, up until x power I, whatever is there. Okay, so I'm just writing this as, okay, where g, I'm thinking of it as this is equal to some gi plus some g tilde, where g tilde is something that is divisible by x power I. Like these are the higher order terms in g, which you don't care about. And I want to know, how do I improve hi? So currently this gi tilde is in the ideal generated by x power I. Okay, are things okay so far? Okay, good. So now I want to know, what should my whatever hi plus 1, what should the next level iteration be? What do I need to do? So this is one of those just do it proofs. I mean, you just try it, see if the equations force you to choose a certain choice. And in many such situations, if you just do one of these things, I mean, the equations will force you to say that, oh, you have to choose hi plus 1 to be equal to something. And that's what we are going to do. So I already have a solution hi. Okay. I'm just going to add some alpha times x power I. Okay. And I'm trying to figure out what sort of alpha can I put here such that my solution improves. Okay. And I'm thinking of alpha as also some polynomial in R of x. We're trying to find the suitable alpha that satisfies. I mean, that works. Okay. So now let's do the following. Let's just basically say, suppose this was my better approximation. Let's multiply it with g and see what the hell we end up getting. Okay. So what is g times hi plus 1 going to be? So this is basically going to be, let's just do this product. It's like this times this guy. So there is one term which is GIHI plus HI G tilde. So in fact, let me write this as HI G tilde X power I. I mean, I know that entire thing was divisible by X power I. I'm referring to whatever the G tilde.
Did you mean HI plus 1 is HI plus alpha X to I plus 1?
Yeah, so I'm just basically now I'm just taking this times G. So I'm just multiplying this guy with this guy.
Is that a typo I'm saying? In this HI plus 1 term, should that be X to the I plus 1?
No, sorry. So HI was currently something which satisfied G times HI was, I mean, where you ignored X power I onwards, then it was, yeah.
Sorry.
Okay, so here you have this times X power I plus what are the other terms? Some alpha times GI times X power I plus there is one of these, whatever, X power 2I terms plus G tilde times alpha times X power 2I. Right? I'm just doing the standard multiplication. Okay. Now, what do I know about this? This was equal to 1 mod X power I. So what does that mean? It means if I multiply these two polynomials, I will get some polynomial which is 1 plus something divisible by X power I. Okay, so let me just write this as 1 plus blah times X power I. Okay, plus these other things, plus H power I G tilde. Okay, let me just take this X power I common. Blah X power I G tilde plus alpha times G of I times X power I plus G tilde alpha times X power 2I. Okay. Now suppose I would like this to be equal to 1 mod X power 2I. Suppose that's what I wanted. Okay. Then this term does not bother me because this thing is already divisible by X power 2I. I don't care about that. But I somehow want to choose alpha such that this becomes 0. Right? Did that make sense? I mean, if this is what you're going for, if you want this to be a much better approximation than what you started off with, you're trying to figure out, can I choose my alpha in such a way that this thing becomes 0? Okay. So if you are forced to make the 0, what would you want to choose alpha as? So what should alpha be? Okay. So let's imagine, suppose this GI was not there. Then what would you choose your alpha to be? You will simply just set it to minus blah, whatever, minus HI G tilde. Okay. The problem is this GI is there. Now, if only you could divide by GI. If you could somehow divide by GI, then you will multiply this with GI inverse times minus blah minus HI, whatever. So now can someone tell me what should I choose alpha to be here? Do I already know of an inverse of GI? You already have computed one already, that is HI. You already have such a thing. So the point is you just set alpha to be equal to minus HI times blah plus H of I G tilde. And you just verify, you just plug this in and just convince yourself that this entire expression will become 1 mod X to the X power 2I. Because substituting alpha equal to this will mean this entire expression inside will basically become 0 plus 0 mod x power I, which basically means this entire expression will become something divisible by x power I. There's already an x power I on the outside. So this entire expression will now end up becoming something that is divisible by x power 2i. Okay, so this is what I mean by the sense of, no, you are coming up with an iterative solution, the sense that you are just saying, currently this is my solution. Let me perturb my solution and ask, what is the best perturbation that works? And you're letting the equation just dictate what you need. I mean, you just write down the equation, and many times you just know precisely what you need. I mean, often this is what you do in various things like gradient descent or whatever. Basically, all of them amounts to, currently I'm at a certain point. I want to do a suitable wiggle around my point and figure out what is the most useful wiggle. And this is just one other version of the same. Okay, so this basically says you set alpha to be equal to this, and what you end up getting is that hi plus 1 times g is now current equal to 1 mod x power 2i. Okay, so which basically means if somebody told you what this hi is, you have a partial solution which was good modulo x power I. This gives you a way of getting a better solution, which is now like it is correct up till degree 2i as opposed to up till degree I. Did that make sense? I mean, okay. And let's also be a bit more precise. How many additions and multiplications did I need in order to compute hi plus 1 from hi? So what, I mean, I need to do one product here, and then I add a bunch of stuff, and then I do another product here. So it's basically some, I don't know, some 2 products or something. Okay, so this is what it amounts to. So therefore, going from whatever hi to, oh, sorry, I should have also mentioned, in order to compute blah, you need to basically compute gi hi and subtract it off from whatever. You need to figure out what is the remaining stuff. That's what that blah corresponds to, right? When I know that gi times hi will look like 1 plus some nonsense, but I need to know what that nonsense is. That's what this blah is. Okay, so therefore this entire thing going from hi to hi plus 1, which this hi, I mean, like the notation was bad in the sense that this is mod x power I and this is mod x power 2i. That is the, whatever, your accuracy sort of seems to keep doubling in some sense. I mean, okay, takes, I don't know, something like 3 multiplications and some additions. Okay, so it's relatively cheap to go from hi to hi plus 1. So overall, it basically says that, you know, in order to compute h right from the beginning, you start with h naught, which was the stupid function, which was just a constant. You started off with that, and then you slowly keep improving what you have. Initially, it was something was there mod x. Next, it will become mod x squared. Then it will become mod x power 4 and mod x power 8 and etc. etc. At some point, you will hit mod x power k. So you will hit this in something like log k steps. So, I mean, you can write this as whatever it takes for PolyMult of degree k things times maybe another factor of log k. But if you stare at this more, you can actually, you can get rid of this and you can basically say this is order PolyMult. Because this is like n log n, this is like n by 2 log n by 2, then n by 4 log n by 4. There is some geometric nature that happens. And you can say that this is at most order polynomial. Okay, so overall, what this tells us is that if we go back to division, this was our original task. Okay, what did we need to do? In order to do this, we basically said, let's first compute the inverse, modulo whatever this nonsense is. Okay, then let's do this multiplication mod this, throw away all the higher degree terms and get q from this. And then we set r to be equal to f minus g times q. And we know that this step basically takes order polymult. This step takes order polymult. This step also takes order polymult. So overall, you took order polynomial. I mean, whatever there was a time that you needed to multiply two polynomials, that's roughly what you took right now. So this basically tells you that you can do polynomial division, like basically as fast as you can do polynomial multiplication.
Just a small detail thing. So in this, here, so this k could be something that's not a power of 2. Right?
Yeah. So the point is, if as long as this k crosses this, that's good enough for you. Because anything that was whatever it was for accuracy beyond this is already good enough for your this thing. So you'll have to do this iterative process, roughly log of n minus m plus 1 many times. Yeah, so that's the number of levels of whatever this iteration that you need to do. And overall, this tells you that you can do polynomial multiplication and division in basically the same time as polynomial multiplication. Like it's just one additional constant factor. Okay, so let's just maybe quickly go over, because this involved many parts of this. Okay, so the first step was we wanted to basically say, this is the equation that I have. I want to get rid of r in some sense. Now in hindsight, let's try to justify whatever we did. I want to basically get rid of r. So I would like to go modulo something. But the problem is this r is not a higher degree term, it's a lower degree term. Okay, because the degree of r is the smallest among everything that's showing up here. So you flip the situation by instead working with the reverse, because now suddenly r is going to be accompanied by a large power of x, whereas the other things are not going to be accompanied by such a power of x. So that's maybe one way to whatever post facto justify why we are doing the reverse business. Okay, so what we did previously was that we basically said, let's just take this equation, which was this equation, and just reverse it and write it down. And the reversal became an equation of this whatever. So if I write reverse of f here, then this is the equation that we ended up with. These two are equivalent statements. And now, because this thing has a large whatever power of x that is sticking along with it, we went modulo a suitable power of x so that that term doesn't bother us. And fortunately, that term, the modulo did not hurt in us recovering q from whatever we got. Okay, so now the task then became, okay, if only I could invert reverse of g, then I'm done. And because g was monic, we knew that reverse of g had a constant term which was 1. So the inverse made sense because of the standard geometric progression thingy that you have. But we were like, okay, can I find such an h quickly? We know it exists, but can we find one efficiently? And for this, what we basically did, what is called Hensel lifting or Newton iteration. These are things that we'll deal with in more generality later on, but this is probably the first time that we are formally seeing this sort of iterative method. And it on hindsight, it seems so stupid that you start off with a solution as basic as h not equal to 1. I mean, you are saying, okay, fine. I mean, I have a solution that sort of works in the sense that at least mod x, it's the right solution. But then can you improve it? And turns out that if you write down the right equation, you know precisely what you need to do to improve it. And so you make those perturbations and stuff. You start with your old h and just add a term which previously you would have ignored. Like had you gone mod x power I, this term would not have mattered to you. But now since you're planning to improve, maybe this term becomes relevant. So, and you're basically trying to figure out what is this alpha supposed to be. And yeah, and it just turns out that there is a natural choice for alpha, and you set that up and the equation works out. So overall, this is what we have. So any questions so far?
Yes, I think like one more way, like maybe throwing some more light is that if like this reversal step was like a bit jarring, I guess, but if suppose someone was able to just give us what r is, and then we just want to find q, then we can like take f minus r is equal to q times g, and then do this modulo. Like then everything else works just as it is, right?
No. So suppose I promise to you that let's say r is 0. Suppose I give you an f, I give you a g, and I tell you that g divides f.
Right.
What would you do there? I mean, I don't have something better to do.
No, then you don't need to do this reverse business, do you? Because I mean, so even then, so we want to find q then.
Yeah, I want to find q. So in a situation where I'm told that f equals g times q, so you are given f, you are given g, and you're trying to find out what q is.
So g is some degree m thing. So we know that q is going to be degree n minus m thing. So if f is equal to g times q, then this thing is true even mod x to the n minus m plus 1.
That's right.
And we know how to find inverse of g even mod x to the n.
No, I know that only when g had a constant term which was 1. Because if g didn't have a constant term, the inverse may not even exist. Like if g was the polynomial which was, I don't know, x power 4 plus something, there's nothing I can multiply where I will end up that looks like 1 plus something. So at some point you need to do this jugaad of somehow making the constant term equal to 1. So it's just that one thing seems to help for two separate situations.
Right.
One, it lets you get rid of r completely so that it doesn't bother you at all. And secondly, it lets you invert the g that you have. So there are two roles that it's playing. Yeah. Okay, good. Okay, so in the remaining about 15 minutes or something, I'm going to ask you the second task, which hopefully I convinced you enough that roots of unities are somehow important. And now I'm going to tell you that they perhaps are not important. Okay, so here is general multipoint evaluation. This was one of the things that we said we'll do in FFT. And we did a very specific version of that. But here is a more general situation. I give you a polynomial as a list of coefficients, and I give you a bunch of points. And I ask you to evaluate the polynomial on all of these points. This is the task. Okay. So just to recall, if this alpha I was equal to omega power I, then this is FFT. For the specific situation where the set of points I give you happens to be whatever powers of a principal root of unity, in that situation, this is precisely, I mean, this is the whatever discrete Fourier transform. And the FFT algorithm is a fast way of doing that transform. But now I want to say, okay, maybe the set of numbers that were given to me were some stupid numbers. Can I still compute this sort of multi-point evaluation quickly? Okay. So any thoughts on how you might want to approach this?
Just like a dart to know that. So could you do some projections thing so that these alpha 0 to alpha n end up becoming roots of unity, and then somehow.
So it's sort of, I mean, in the sense that one of the things that roots of unity must satisfy is that their lengths or the norm must be equal to 1.
Oh, so okay,
if they happen to be, I mean, for example, if they are arbitrary integers,
yeah,
I mean, then I don't have a good way of doing that, unless, I mean, but in general, I don't know how to do that. I mean, you might say that you go modulo a suitable thing, and then maybe 2 power n becomes 1 mod whatever you are going modulo or something. I don't know how to do this in a systematic fashion. Sorry, Saurabh had a question?
No, I am saying firstly you have to extend the f, right?
Yeah. So, I mean, let's say, I mean, like at this point, I mean, like, I just want to do this for general alpha 1 through alpha n. Maybe FFT is not the right way of doing it. But somebody has told us that polynomial multiplication can be done quickly. It can be done in n log n log log n. And I just want to use that. Okay. So, I mean, this is a tricky thing, but hopefully I'll give you a few hints and you can catch up on this thing. So this is the list of points I'm given, alpha naught through alpha n. I'm supposed to evaluate. Okay. By the way, this setup works only when the number of points equals the number of coefficients. Otherwise, you artificially bloat up one of them to make sure they are the same. I mean, just pretend that, this is actually a larger degree polynomial with zeros, or you just evaluate it on a few more points. I'm using the same n to work for both. So anyway, so this is what I have to evaluate on these points. So I'm going to try and do a divide and conquer. Okay. I'll split this into two halves, and I'll call the left half as alpha L. I'm just abusing notation. Alpha L is actually a set right now. Okay. And the right half, I'm going to call it alpha R. So the first, I don't know, n by 2 elements are in alpha L. The last n by 2 elements are in alpha R. Okay. Now, here is a template of the algorithm I'm interested in. I want to recursively call the multipoint evaluation on some suitable polynomial FL. I don't know what this FL is supposed to be. Okay. But I would like FL to be a polynomial of degree n by 2, on which I'm going to ask you to evaluate on all points in alpha L, which is also another set of size n by 2. And similarly, I want to do this for FR and alpha R. Like basically sort of assign the task of evaluation to these two polynomials and somehow return something. I don't know what is the natural thing to return. Okay. Now let's be super wishful and say that I'm just basically going to return gamma L, gamma R, by which what I mean is I'm supposed to return n evaluations. I will return whatever were the evaluations in the first part and whatever were the evaluations in the second part, just concatenated as lists. Okay, just put them together and just return. I don't know what's the. I'm going to put comma here, but hopefully you know what it means, because if I put plus or dot or whatever, they all seem to have other meanings. Yeah. Okay, so this is the template of the algorithm that we have in mind. And what I want to know is what should FL and FR be? If I want this algorithm to succeed, okay, what would I want FL and FR to be? Okay, so let's ask ourselves the following. What are some constraints that you think FL should satisfy and FR should satisfy? So the first item here, the first index in gamma L, is supposed to be the evaluation of FL at alpha naught, because that's what the multipoint evaluation will return. I am somehow saying that is also the evaluation of F at alpha naught. Which means what I would like is that F's evaluation on the left half agrees with FL's evaluation on the left half. And similarly, F's evaluation on the right half agrees with FR's evaluation on the right half. Okay, so I'm just writing that down here. This is what I would want. I would want to choose FL and FR such that these two conditions hold. Okay, so now do you have a guess of what FL and FR should be?
So the elements of alpha L are the roots of F minus FL.
Precisely. So this basically means that when I look at F minus FL, I want this to be, must be divisible by X minus whatever, this X minus alpha I whenever I is in whatever the left half.
Is that why you wrote ideally?
I mean, actually, okay, I didn't intend to write it that way, but so if alpha I is in alpha L and you look at this product, okay, then I would like this guy to be to divide this thing, which basically means whenever I substitute X equal to any of the alphas on the left hand side, then I want these two to evaluate to the same value, which means I want this to be equal to 0. So this is another way of basically saying that I want F to be equal to FL mod this thing. Okay. And similarly, I would like f to be equal to fr mod the right hand side. Alpha r of x minus alpha. Is this okay so far? I mean, like, is okay. So the algorithm is now clear. Let's first compute these products. Okay, let's call that as GL and let's call this as GR. Okay, and I'm going to compute FL to be F mod GL. What does this mean? It's just saying compute the remainder of F when you divide by GL. GL is fortunately a polynomial of degree n by 2. I mean, whatever this thing is, right? So therefore, the remainder is something of degree strictly smaller than n by 2. So FL and FR are both polynomials of degree about half what you started off with. Okay. And now you do the task, I mean, basically the same template we had last time. You do the multipoint evaluation of FL and FR separately and put them together. Okay, is the algorithm clear what you need to do for this? I mean, you're just setting it up in such a way that if I were to break up the problem into two other subproblems, where I have two polynomials and somehow their evaluation should match what I want, you sort of, your hands are tied. You basically have only one choice that you can choose at this point. So that tells you precisely what FL and FR are supposed to be. So you run recursively the multipoint evaluation on those 2 points, sorry, those two polynomials, and just concatenate the answers and return. So the problem is just about, we need to just convince ourselves that this entire thing, I mean, does not take too long. So it roughly looks like, I mean, so the important part is like, how much time does this take? Okay. I'll let you convince yourself that this, okay, it should be easy to see that this is basically PolyMult plus some additional maybe log n factors or something. But maybe I'll let you play around to see if you can save those log n factors. You know, do you really incur a log n factor? The most natural thing to do is like, you know, think of this as a big binary tree where you're multiplying two things together and then multiplying those two, etc., etc. Right? You take all pairs, multiply them, and then you just need to count how many multiplications did you do, and was it something that you can tolerate or not. Okay, I let you convince yourself that this actually will take O tilde of PolyMult of n. Okay, so what is the overall running time going to be? There are two recursive calls of n by 2 plus a little bit of PolyMult here. And this is like n polylog sort of factors. And if you solve this recursion, you will now end up with one more additional log factor, which anyway we are ignoring. I mean, we are going to write this as O tilde of poly. Okay, and this tilde just refers to the fact that I'm ignoring log factors of whatever was the operand. Okay, so O tilde of n is like n polylog n. Like I don't care about extra log factors. So in some sense, this basically tells you that previously we were saying that for FFT, where the set of points on which you are evaluating happen to be powers of a principal root of unity, for those things, you can run this algorithm in n log n time. But this basically says if you're not particularly you don't particularly care about these extra log factors, well, there's nothing special about these roots of unities. You can actually do multipoint evaluation on any set of points in roughly n time, like ignoring polylog factors. Okay, and it just uses your whatever the computing remainders, etc., and then just using them as black boxes in some sense. Okay, and I'm going to give you a spoiler for the next problem set. This will show up in the problem set the next time, which is you can actually do the same thing even for interpolation. Okay, which is the task. Suppose your task is I give you a set of points and the images I'm interested in. I want you to build a polynomial such that on each alpha I, f of alpha I equals beta I. That is, this is like the inverse of the multi-point evaluation. Okay, like I give you the points and its evaluations. Can you figure out what the polynomial is? And turns out that also you can do in near linear time. And basically you have everything, you've seen everything that you need for that. Okay, and this will be something that will be there in your problem set. The next thing. Okay, so this sort of concludes the basic algorithms involving polynomials, like just addition, multiplication, division, etc. So from the next class onwards, we will start moving towards factorizing polynomials. And there, we will often be happy if we can do this in polynomial time. We won't be so stuck up to come up with a near linear time algorithm, etc. So yeah, so that's what we will start from the next lecture onwards, and we'll slowly build up the necessary theory, etc. we want for this. But the sort of iterative methods will start becoming very, very useful. Because often the way it will work is like you will try to find roots by successive and successive approximations. So that's sort of how it will show up. And anyway, we'll see the details of the next lecture onwards.
I have a small question.
Yeah, go ahead.
So in case of extrapolation, will it take also same time?
Sorry, what is extrapolation? I mean, like.
So suppose the points we are working in Rn, and the points you are evaluating on alpha 1 to alpha n, where it's in alpha 1 less than alpha 2 less than equals less than dot alpha n, right?
Okay.
So if you take any point outside from the interval alpha 0 comma alpha n, then what will be the value at that point? If we try to.
So are you told what the images of these things are?
Yes.
So then you can do the same thing, right? You first, given the images, you compute the polynomial completely, and then evaluate it at whatever you want.
But maybe he's asking, is that, I mean, that is, we're doing something stronger.
Oh, you're
so I am trying to say, I am trying to say that, so suppose you are working in a real polynomial, okay? So we have given an interval a comma b, and we have given any points, n points from a comma b and corresponding the functional values. We already got the function that you said. Now we have given fx comma if alpha I comma f of alpha I, where I equals to 1 to n, where alpha is taken from the interval a to b.
Yeah.
So if I take any point outside of interval a to b, or just like that, take any point less than alpha naught, the smallest alpha where we evaluated. So the functional value may not be exact, right? Because we are doing the interpolation.
So maybe I'm not following it. So once I know alpha i's and beta i's, so beta i's is the value of f at these alpha i's. I can precisely find out what f is, right?
Yes.
So that, I mean, this particular task tells you that you can do this in nearly linear time.
Yes.
Right. And now I'm saying that once you find what f is, now you say you have a different point gamma in mind. And you want to evaluate f on gamma.
Yes.
So that is again basically n such multiplications or something.
Okay. I'll discuss you in offline.
Okay. So then maybe the model is slightly different or something.
I'll discuss you in offline.
Okay. So if there aren't any further questions, then we'll stop now and we'll meet on Thursday.